Hello everyone, my name is PM Jodoin, and today we'll be talking about the basics of deep learning and neural networks, part 1. I'm a professor at the University of Sherbrooke, Canada. So before we dive into the mathematics of neural networks, we'll start with a very simple example that most of you will understand right away. It's an example that is held in a hospital where a patient that comes to this hospital are either healthy or sick. And to figure out if a patient is healthy or sick, they all undergo the same acquisition protocol, which boils down to measuring their body temperature and cardiac frequency. Now, if we do this with patient 1, well, patient 1 would be associated to two values, its body temperature and cardiac frequency. And eventually, since a specialist would look at the patient, we will end up with a diagnostic if this patient is healthy or not. Then a second patient will come, will measure his body temperature and cardiac frequency, and a specialist will also figure out if this patient is sick or not. And we'll do this in time for the first n patients that will show up at the hospital. Now, if we do this, this table here, we'll call it D for the rest of this presentation. And this table has two columns. The column X, which corresponds to the input data, the body temperature and the cardiac frequency. So X is a 2D vector of two real values. And the diagnostic will be recognized as the letter T, or said otherwise, is the so-called target. So the target is a binary value, sick or healthy. Now, if we consider D for what it is, well, it's essentially a set of points where each patient is a point in a two-dimensional space. X-axis is the body temperature, and the y-axis is the cardiac frequency. And the circles stands for the healthy patient, and the stars for the sick patient. Now, in our example, later on, a new patient comes to the hospital, and we would like to figure out if that patient is healthy or not, without having a specialist to figure out what is the true diagnostic for that person. So how can we do this? Well, we will have this patient undergo the same acquisition protocol. So we'll measure his body temperature and cardiac frequency, and we'll quickly realize that this patient will fall somewhere into this feature space. Now the question is, how can we determine the status of that patient? Is that patient sick or healthy? Well, one easy way would be to look at the nearest neighbor in the feature space, and we'll figure out that since most of the nearest neighbors are stars, well, this red dot is probably associated to a sick patient. But there's a different solution to that problem, which boils down to divide the feature space into regions, the sick and the healthy regions, pretty much like this here. So if we knew the equation of this line there, it would be very easy to mathematically separate the space between the healthy and the sick patient. So we will have a healthy region and a sick region. So any point that falls into this red area would automatically be associated to a sick patient, whereas points that falls into the green areas would be associated to a healthy patient. And this brings us to this letter y, which is a function that we call the classification function that is given a point into a two-dimensional space, x, a vector, and returns a binary value, either healthy or sick. Now the question is how to split the feature space. Now, as I said, this is the equation of a line, so the equation of a line doesn't seem to be too complicated. But how do we relate the equation of this line to a classification function y that can return either healthy or sick? Now, to answer this question on how to split the feature space, let's go back to the very definition of what a line is. So you might remember from your early days in school that the equation of a line is given by y equal mx plus b, where m is the slope and b the bias. And the slope is computed by taking the ratio between delta y and delta x. And b is the bias, which is essentially the distance to the origin. So if the red line was to cross the origin, then b would be equal to 0. Now, if we replace m by the ratio delta y over delta x, we'll still have the definition of a line. Just replace m by its own definition. Something we could also do is to get rid of the denominator here by multiplying both sides of the equation by delta x. This would lead to the following equation. And we could also take these two terms here and put it on the other side, and we would have an equation that looks like this. So every non-zero values would be on one side, and on the other side we would have 0. So this is the definition of a line. I just took that first equation here and just reformulated some terms. And something I'm also going to do is to rename some variables because it's more convenient to have W1, W2, and W0 instead of having delta X and delta Y's showing up everywhere. So that would lead to the following equation, which is still the equation of a line. Something else I would like to do is to replace or rename X and Y by X1 and X2 because this is a feature space, and for now we have two features, the body temperature and the cardiac frequency, but eventually we would like to have more features. For example, we would like to have 3, 4, 5, 6, 7 n features, and this way it would be more convenient to have X1, X2, X3, X4 all the way to Xn. So that would be more convenient. So in this way, we have this equation, W1 X1 plus W2 X2 plus W0. Now this equation here is still the equation of a line. I just reformulated the first definitions of a line that we had into something a little bit more different, but still this is the equation of a line. Now what's very interesting is that if you look at this here, this equation says that any point that falls onto this red line should have this equation here return 0. So instead of having 0, if we have y equal to this equation here, well, this y function should return 0 each time a point falls onto the red line. Something interesting is that this red line has a normal which is perpendicular to it, and this normal we can demonstrate. The demonstration is not very complicated. We're not going to do it here, but in fact, the normal is given by W1 and W2, the first two terms that multiply X1 and X2. Now, interestingly, if you feed this equation y with a point that is not on the red line, but instead is in front of the line, and I say in front because it's on the side of the normal, then this equation will return a positive value. And if, on the other hand, we feed this equation by a point that is behind the line, so on the other side of the normal, this function will return a negative value. So just to and this is what we call the classification function. Y is a classification function, and we'll see it very soon. So for example, if we take an actual example where W1 is equal to 1, W2 equals to -2, and W0 equals 4, then if we take a point that falls onto this line and we replace W1, W2, W0 by these three values and X1, X2 by those two values, we'll quickly realize that indeed Y equals to 0 because this point falls onto the line. However, if we feed Y with the following point, 1, 6, and replace all of the values of this equation by these three values and 1 and 6, we'll realize that the equation is equal to -7, a negative value. And if we feed the equation by 4 and 1, we'll see that the equation returns 6, which is a positive value. Now, interestingly, this classification function, which in fact is simply an equation of a line that returns a positive value each time a point falls in front of the line and a negative value when it falls behind the line, can be summarized by the dot product between two vectors, the vectors of what we call parameters W and the vectors of input values. So 1 is just to multiply the bias W0, but X1 and X2 are actual measures, actual data that was gathered from patients. And so this is the equation of a dot product, which also can be represented as the product between an horizontal vector and a vertical vector here. If you do the vector-to-vector multiplication, this is also a dot product. Now, for simplicity, we'll drop the prime here because the prime is to account for the fact that we added a 1. But for simplicity, we'll drop it and assume that X always contains a 1 in order to account for the bias. So it's very important to understand that a linear classification is nothing more than a dot product with a bias included in X. And the dot product can be represented as the multiplication between two vectors. Now, in machine learning, there's the notion of learning. And what does learning mean? Well, from our simple example, it boils down to the process of starting from a dataset D that we will call the training dataset, and to find the parameters W0, W1, W2 that would best separate the two classes. A priori, we do not know what these parameters are, but with the help of the content of the dataset D, we would eventually be able to find the correct values for W0, W1, and W2. So how do we know if a model is good? So this is a very good question. How does an algorithm knows that this model is good, but that other model is not good? Well, the only way of coming out with a solution for this problem is throughout what we call the loss function. So a loss function is a function that returns a very small, if not zero value, when a linear function or a classifier can successfully separate the elements of every class. So in our case, the healthy and the sick patients, like you see on the left. Now today we'll see three different algorithms associated to very well-known neural network concepts: the perceptron, logistic regression, and the multi-layer perceptron. So the perceptron is not something new. It was in fact first published in the 1950s by very well-known Frank Rosenblatt. And the perceptron is directly related to what we have been talking about in the last couple of minutes, which is the definition of a line that you can relate to the dot product between a set of parameters W and input data X. But the perceptron has this characteristic, is that most of the time we picture the perceptron in a graphical way, as you can see here on the left, where first on the very left here we have the input data, so 1 for the bias, X1 and X2 for the body temperature and cardiac frequency. Now then we have arrows, and each arrows are associated to a parameter, W0, W1, W2, and this dot here is nothing else than the dot product between the vector X here at the input and the parameters W. Now this is absolutely equal to the equation of a line that we have seen before. What the perceptron adds is what we call an activation function. In the case of the perceptron, the activation function is the sign function, which returns +1 when sign is fed with a positive value, and -1 when sign is fed with a negative value. Now if you combine this together, so a dot product and an activation function, and you put these two into one single operation, well, we call this an artificial neuron, which in fact is nothing else than a dot product and an activation function. And an activation function is a nonlinear function, and we will see later on during this day other types of activation function. Now so far what do we have? We have a training data set D, a classification function, which is the definition of a line, that in our case we will now represent as a graphical model like this, the perceptron model. We have a loss function that we haven't seen exactly what it looks like so far, but we'll look at it very soon. And then we have a training algorithm that finds the best parameters that minimize the loss function L. Now obviously linear classifiers have limits. For example, it doesn't work well on non-linearly separable data. In fact, if you are to use a linear classifier on the kind of data like this, you would get a very large error. Now, to deal with non-linearly separable data, three classical solutions have been proposed. The first one is to acquire more observation. The second one is to use a nonlinear classifier, and the third one is to transform the data. We'll look at what it means to acquire more observation. Well, in our little example, we were acquiring two different values, so the body temperature and the cardiac frequency. And maybe after all, this is not enough, and this is far too simplistic to come to the conclusion that a patient is healthy or sick. So instead of this, we might decide to acquire more data during our acquisition protocol, and we'll be, for example, on top of body temperature and cardiac frequency, we'll ask the patient to tell us if he or she is suffering from some headache, and give a value between 0 and 10, for 0 being no headache and 10 being an intolerable headache. So if we do this, instead of having points that fall into a two-dimensional space, we would have points that fall into a three-dimensional space. And as you can see here, if this third dimension, or this third set of value that was acquired, is correctly chosen, then we might be able to fit a plane between, because now we're in a three-dimensional space, we could be able to fit a plane between the red dots and the blue dots and to correctly separate them. Now on the left we had the equation of a line, where, well, on the right we have the equation of a plane, which is very similar to the equation of a line, except that it has a new term, W3 and X3, to account for this new third dimension. Now, this is the equation of a line that I gave before, with here the dot product and the nonlinear activation function that is very typical of the perceptron. Well, if you add the third dimension here, so how do we train a perceptron? Well, let me remind you what training is. Starting from a training dataset D, which contains a pair of data and target, X and T, the goal is to find the best W's such that our model Y, which is the equation of a line in 2D, of a plane in 3D, and an hyperplane in more larger dimension, this function here should return the correct prediction. And the correct prediction for xn is the target n. In other words, the goal is to minimize the training loss. The goal is to have a W that will minimize the loss of the prediction made by the model, giving the correct target for every data n in our training data set. Now, if we want to do this, we have to solve a so-called optimization problem. Now, again, considering the fact that a loss function is low for a good solution and large for a bad solution, and a good and a bad solution are all linear solutions, but with different weights W. So if we look at, for example, I took a very simplistic case where we would have only two parameters in our model, and for each possible combination of parameters, we would compute the associated loss to it. We would see that if we could do this, well, we would see that the loss is minimum where the best solution is, so the best combination of W1 and W2 is, and the loss would become large for bad solution. So the goal of training, whether it is a perceptron or any other neural network, is to find the best solution. And the best solution is where the slope of this function here is equal to 0, or if you prefer, where the gradient is equal to 0. The gradient means the slope in the x and y coordinate, or along the W1 and W2 axis. Now, to do this, we could implement the following algorithm, which is very well known. It goes as follows. It starts with a random initialization. So you take a random W1, a random W2, and by considering that solution, very likely that solution will have a large loss. However, since L hopefully will be a function that we can derive, well, we can find its local gradient and move that point in the opposite direction of the gradient. So the gradient is the direction towards which the function increases the most. If you take the inverse of that gradient, so minus the gradient, that will point towards a direction where the loss decreases the most. So if you take a step, that will move the point towards a little bit more close to the optimal solution. And if you do this again and again and again and again in a iterative manner, you will eventually or hopefully reach a global minima. So to do this iterative process, we call this algorithm a gradient descent algorithm. And the gradient descent is nothing more than this. We take the parameters of our solution at iteration k, and we subtract from it the gradient of the loss function with a certain learning rate. So the learning rate determines the step size. So how large do we, what is the step size between two steps that we make during the gradient descent? And we do this by combining this, and that leads to a new solution for W. So at iteration k plus 1. Now the perceptron has a loss which is called the Perceptron Criterion, and the Perceptron Criterion comes from a very simple observation. A wrongly classified sample is one for which the score of the function, so the function is a dot product, the score of that function would be, for example, positive, but the true target is negative, or the other way around. The score of the function is negative and the true target is positive. Now, consequently, if you take minus the dot product, so the score of your function, times t, which is either +1 or -1, this function here is always positive for wrongly classified samples. Now let me say this again. If this is negative and this is positive, multiplying the dot product by t will lead to a negative value, but since I have a minus here, this will lead to a positive value. Same in this configuration here. The dot product times t is negative, times -1 is positive. So this function here is always positive for wrongly classified samples and always negative for correctly classified samples. Now that's the equation of our perceptron loss, which is the sum over every wrongly classified sample. And since this for every wrongly classified sample is always positive, then the more wrongly classified samples you have, the larger the loss will be. And at the limit, if every sample is, so every sample X is correctly classified, so that means V would be empty, and if V is empty, then the loss function here will be 0. Now, for example, if you take a configuration like this and you compute the loss function, you'll get a relatively large value, such as 464. If, on the other hand, you had a better solution that would linearly separate the blue dots from the red dots, you would have a loss of 0 because you would have no elements in V. Now, the gradient descent, that's the equation of the gradient descent, can be illustrated like this. And this is a so-called stochastic gradient descent algorithm. So we start by initializing W, typically by using random values. We start by k equals 0, and k is an iterator. And we start iterating, and at each iteration, we go through every element in our training data, and we move along the opposite direction of the gradient. So the perceptron loss is the following. So if you want to compute the gradient of L with respect to W, since this equation here is linear with respect to W, it's only this, the gradient. So it's the same function without the W because it's linear with respect to it. So the stochastic gradient descents become the following function, which is very easily implementable. We start by initializing W again, by setting our iterator to 0, and then we iterate throughout each training data from n equal to 1 to capital N, and then we look if the data is wrongly classified. So this is negative when it is this product of 3 terms is negative when a data is wrongly classified, and if it is wrongly classified, then you move W by a step of eta in the inverse direction of the gradient. So the inverse direction of the gradient is minus, so it's t times x. And here we don't have a summation because it's just one element we're looking at. So the learning rate here, essentially, as I said, determines the speed at which we will converge. So if eta is too low, we will have a slow convergence. If it's too large, it might not converge very well. It might even diverge in some cases. So eta is a very well-known so-called hyperparameter that we need to tweak before to find the right value. In some implementation, we can have eta decrease at each iteration, for example, by starting with a large value of eta, and as the stochastic gradient descent iterates, we get to set a lower and a lower learning rate, as you can see here. So we have similar loss functions. For example, this one is the Perceptron Criterion. Well, that criterion is a summation over every wrongly classified samples. We could have this function here that we sometimes see in the literature, which is a sum over every element in the training data. But instead of accounting for this function, we account for the max over 0 of that function. So if you iterate over a correctly classified sample, this function here with the minus will return a negative value, and max of 0 over a negative value is 0. So these two equations here are mathematically equal. You could add a 1 here. So these two equations are almost identical. The only difference is here we have 1 minus this, whereas here we have no 1 in front. And this function here is called the so-called hinge loss or SVM loss. So we don't have much time to discuss why there's a 1 here. I suggest you to go in the literature and look for the SVM loss to figure out why. It all boils down to the notion of margin. So far, what do we have? We have a training data set. We have a linear classification function, which may be in a 2D, 3D, or as we can see here, in an m-dimensional space. We have a loss function, and here we define the Perceptron Criterion, but we could also use the ING loss function or the SVM loss function. Obviously, the linear classification is a neural network, which accounts for a dot product and a nonlinear activation function. And we have a training algorithm, and the training algorithm is a gradient descent algorithm, or a stochastic gradient descent algorithm, whose goal is to find the best W's, and the best W's corresponds to a configuration where the gradient of the loss with respect to W's is equal to 0. So far, we have seen a two-class classifier, but obviously not all problems are two classes. For example, you could have a problem where you have healthy patient and the patient suffering from disease 1 and patient suffering from disease 2. So that would lead it, that would be a three-class problems. And obviously, you could have more than three classes. You could have 5 or 10 classes. Well, the good news is that the perceptron generalizes to more than two classes very naturally, pretty much as naturally as it did generalize to more input dimensions, as we have seen before. Now, in this case here, we have a very simple multi-class or three-class linear perceptron, where on the left, we have the input data, one for the bias, and x1, x2, x1 being the body temperature and x2 the cardiac frequency, and each of those neurons, which for now do not have any activation function, but they embodies the dot product, and as I've mentioned before, the dot product is the equation of a line. So we have 3 neurons here because we have 3 classes. So for example, that dot product could represent the equation of that red line over here, that second dot product, the green line over here, and the last dot product, the blue line over there. So if you unroll all of these equations, that leads to this equation system. And at the end, when the system makes a prediction, you would have 3 outputs. And it's the output that has the largest score, so the largest result of the dot product, which would tell which class to assign this value x to. So all of this red area contains every point where if you take the coordinates of a point, feed it to the system, well, the output for the red class is going to be larger than the output of the other 2 classes. And same for this green area and the blue area. Now, since this is a linear system, we can represent this as the multiplication between a matrix W, which contains the 9 parameters. And again, why do we have 9 parameters? Because we have 9 arrows. 3 over here, 3 over here, and 3 over there. So the number of parameters in the network is directly related to the number of arrows that we have between neurons. And these 3 parameters there correspond, for example, to one equation, and the second set of parameters to another equation, and so on and so forth. Now let's take an example. Let's say, for example, we have a point that is at position 1.1 and -2. This is a hypothetical example. And if this is the set of parameters of our system, and we multiply this 3x3 matrix by this 3x1 vector, we will end up with a 3x1 vector where 2 of the output are negative. So the output of the green class and the blue class are negative because this point falls behind those classes, as you can see with the little normal arrow there. And one of the class is positive, and this class is class 2. So you would conclude that if this system is properly trained, this x value is associated to class 2. Now the loss function of the multi-class perceptron is something that somewhat resemble the Perceptron Criterion we have seen before. So it's the summation over all wrongly classified samples, as you can see here. And for each wrongly classified sample, you take the score of the wrong class minus the score of the correct class. So Tn is the correct class index times x. And you would see that this is typically wrong when the score of the wrong class is larger than the score of the correct class. That's why it is wrong. So this minus that is always positive. And the more wrong a score is, the larger the loss will be. Now the gradient of the loss with respect to W, since W is linear, so there's no square over here whatsoever, it's going to be something like that. It's a score over the correctly classified sample times x. Now, the stochastic gradient descent algorithm of the multi-class perceptron is as follows. First, we initialize our, let's say, 3x3 matrix, start iterating for a certain number of time, and then we start visiting every point in a training data set. And for every point, we look at the class which corresponds to the largest score, as I mentioned before. And if that class is different from the real target, then you may conclude that this is a wrongly classified sample. And so if this is wrong, then we will update the parameters of the wrong class as well as the parameters of the correct class. Why these two? Because this equation here for that example there that is wrongly classified only involves the parameters of two classes. So the perceptron has lots of very appealing advantages. First, it is very simple. Second, it does not assume that the data follows a particular distribution. It doesn't assume like certain algorithms that your data is a. Now they are. So two famous ways of improving the perceptron is either to consider a different activation function with a new loss, or to just redefine the architecture of the network. In the first case, we end up having a so-called logistic regression. In the other case, it's a multi-layer perceptron that we will eventually get, and a convolutional neural network. Now, let's first start with the logistic regression. So the logistic regression is very similar to the perceptron. If we go back to our initial example where the goal was to linearly separate patients that are healthy from patients that are sick in a two-dimensional feature space, we mentioned that the decision function is nothing more than just a simple dot product, as you can see here, followed for the perceptron by an activation function called the sign function, which would return +1 or -1. So it was a function that returns a binary value. Here the sigmoid is a little bit different. The sigmoid is the activation function corresponding to that equation here. So the equation is 1 over 1 plus e exponent minus t. So if t is equal to 0, then this function is 1 over 1 plus e exponent 0. So it's 1 over 1 plus 1, which is 0.5. And when t gets very positive, then we have a sigmoid function that contains 1 over 1 plus e minus a large value. So this quickly goes to 0. So we have 1 over 1. So it tends to to eventually reach 1. And when t gets very negative, then sigma returns a value very close to 0, because e exponent minus a large value is, at the end of the day, e exponent a large value. And so the denominator becomes very large, and sigmoid tends to 0. Now, when we combine the sigmoid function and the dot product, this leads us to an artificial neuron, because again, an artificial neuron is nothing more than a dot product followed by a nonlinear activation function. And in the case of this neural network, the output of the neural network is the sigmoid of the dot product. So again, if the dot product returns 0, which means that the point x1 and x2 falls onto the line, the red line that we have mentioned before, then we'll have sigmoid of 0, and sigmoid of 0 is 0.5. So the output of the machine there, the neural network, would be 0.5. And if the dot product is very positive, then the output of the network will be close to 1. And if it's very negative, the output will be close to 0. So this is illustrated here. If we have points onto the separation line, the output is 0.5. If we have points in front, the output will tend to 1. Otherwise, it will tend to 0. Now let's look at an actual example where W contains, the vector W, the vector of parameters, contains 2, minus 3.6, and 0.5, and X is some point in the dimension, the 2D feature space, and 1 is the bias. So if you compute the dot product between those three values and these three values, that would give you minus 1.94, and the sigmoid of minus 1.94 is given by this equation here, which corresponds to 0.125. And since 0.125 is lower than 0.5, then we can conclude that xn is behind the plane. And so it is associated to the class behind the plane. Now, like the perceptron, the logistic regression accommodates for as many input features. So here we have k input features plus 1 for the bias. And with this machine, we may ask ourselves, what is the loss function? Well, the loss function is necessarily different than the Perceptron Criterion, because this is not the same equation than for the perceptron. One thing that is very interesting with this sigma activation function is the fact that it returns values between 0 and 1, just like a probability function. And in fact, if I go back here, you can see here that if you have a point that is way in front of the separation line, the score of the value tend to be 1. So that means the probability of that point to be in the circle class will become almost equal to 1. So the system will be very confident, so it will assign a large probability of being assigned to this class. Whereas on the other hand, if a point falls far behind the separation line, then the probability of being assigned to the circle class will fall to 0. And if a point is exactly on the separation line, then the probability of being assigned one or the other class is 50-50, 0.5. So when using an sigmoid activation function at the output of our network, it turns our network into a system that models this conditional probability distribution function, which can be read as the probability of having a class C1 given, so the pipe here can be translated in English by given the input vector x. Of course, if you want to know what is the probability of having class C0 given x and the parameters w, it's simply 1 minus the output of the system. Why? Because the sum of these two probabilities needs to sum up to 1. Now, without getting into the mathematical details, the loss function of a machine like this one here, due to the very nature of the conditional probability distributions that we have here, and if we assume that the data follows a certain distribution function called the Bernoulli distribution function, if we assume this and that we want to maximize the probability of having the correct class, then the loss function is something called the cross-entropy. And you might want to keep this in mind because the cross-entropy is by far the most well-known and most used loss function in neural networks. So this is a two-class cross-entropy. In a sense, it does make sense. It's a little bit complicated, but it's the log of the output of the system. Now, if the true class is 1 and the output of your system is also 1, then the log of 1 it is 0. And if the true class is 1, well, 1 minus 1 is 0. So that term is cancelled out, and you end up having 1 times the log of 1. So at the end, this is 0. So then that gives you a loss of 0, at least for this n example. And if, on the other hand, the correct class is 1, that is 0, so 0 times this cancels out, plus 1 minus 0, it is 1. And if your output, the output of your system is also 0, you'll have log of 1 minus 0. So again, you'll have log of 1. And the log of 1 is 0. On the other hand, if your system makes a very bad prediction, for example, if the class label is 1, but your system returns a value very close to 0, then you'll have 1 times, so the second term is cancelled out because you have 1 minus 1. But here you would have 1 times the log of a value close to 0, and the log of a value close to 0 is a very negative value. At the limit, it could be minus infinity. That's why we have a minus here. So you would have minus the log of a very negative value. So minus a log of a very negative value. That would become a very large value. So this way, the better your system is, the smaller the loss, the cross-entropy loss will be. And we can also demonstrate, and we're not going to be doing it, but the derivative of L with respect to W, if you prefer, the gradient of the loss with respect to the weights, is given by this formula here. And so, and as you can see here, as opposed to the perceptron, the gradient does not depend on the wrongly classified samples. So any sample, even if it's well classified, will contribute to the gradient. And so the system will not be trapped with possibly an infinite amount of solutions that are all quote-to-quote perfect, as it is the case for the perceptron. So the big advantage is that with the logistic network is that it is more stable than the perceptron. Here we have 3 different solutions that I obtained with the perceptron with different initialization method. And as you can see, these 3 solutions are all different, but according to the perceptron, they're all perfect. Whereas with a logistic regression, it systematically almost always converge to this solution here, which is very well positioned between the distributions of the blue points and the distribution of the red points. So you have more stability with the logistic network. And also it's more effective than when the data is not linearly separable. It doesn't jiggers as you would have with the perceptron. Now, what if you have more than 2 classes? Well, the idea is pretty much the same than the multi-class perceptron. So you would have an equal number of, you would have as many output neuron than you have class. So if you have a 3-class problem, you would have 3 neurons at the output. But you would add a little something that is very important. This is another buzzword that you want to keep in mind. It is called the softmax. So essentially, you take the exponential of the output of each neuron here, followed by a normalization. Now, if you do this, if you take whatever the score that neurons return, takes the exponential, and then divide by the sum of these 3 exponential, then the output that you would get here would be something like this, right? It's the exponential of your dot product divided by the sum of the exponential of every dot product for every class. That's what you have here. And this, again, can be seen as conditional probabilities. So this would be the probability of having class 0 given the weights of the weights of the network and the input vector x. And this would be the conditional probability for class 1 and class 2. So this is very appealing because you have a system that can automatically model this conditional probability distribution function. So that's very nice. So this is called the softmax, and a lot of neural networks now work in, especially classification neural networks and segmentation neural networks, as you will see later on during this class, use a softmax. So please keep this in mind. When you use a softmax for many classes, the class labels become what we call the one-hot vectors. So for example, a very well-known data set called CFAR10. So this is an old data set that people are still using. It's very easy to download from the internet. It contains a couple of tens of thousands of images, all distributed according to 10 different classes: airplane, automobile, bird, cat, and so on and so forth. And each class, instead of being associated to a value like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it is assigned to a so-called one-hot vector. So it's a vector of 10 elements. Every element are equal to 0 except for 1 that is set to 1. So airplane is the first class. So the first element is equal to 1 for this class. The second class is automobile, so the one-hot vector associated to it is a set of zeros, except for the second position where we have a 1, because second position, because this is the second class, and so on and so forth up until the very end. Now this one-hot vector distribution can be seen as also a probability distribution, but with a 100% chance associated to a certain class. And this echoes to the fact that the output of a multi-class neural network, which with a softmax at the output, is also a series. It's also a probability distribution function, with value close to 0 for some classes and value close to 1 for other classes. Now the cross-entropy loss for multi-class case is something given like that. Again, the log of the output of your network times this t-value, and this t-value is always equal to 0, as you can see here, except when you have the correct class for a certain element n. And we can also demonstrate that the gradient with respect to w of this loss is given by this function here. So hopefully the you will not have to implement these. It all comes with the deep learning libraries like TensorFlow and PyTorch. Something else to keep in mind is that most of the time our loss function would come with a so-called regularization function. So what is this? If you take the input value x here, which contains 1, 1, 1, so all ones everywhere. Well, the dot product between x and w1 and the dot product between x and w2 is going to give you the same score. And that's not normal. These two solutions are different, so they should be given different loss functions. So which weights are the best? So typically, we tend to favor the weights, the sets of weights whose values are the smallest. And this gives rise to a so-called maximum a posteriori solution. So instead of just minimizing the loss function here, which, for example, could be cross-entropy, we will always add a regularization term r times lambda, which is an hyperparameter that, again, we need to tweak. And so this is a constant that we need to set a priori before we start training our algorithm. And the second term here is the regularization. And the regularization is typically a L1 or L2 function. So that means L1 is the sum of absolute value in the W matrix, in the W matrix. And here would be the sum of the square values of every element in the W matrix. So that's a lot of information. Let's recap what we have seen before. So we start by looking at two-class neural networks. So on the left, we have the perceptron with the sign activation function, which return plus and minus one, plus 1 and minus 1. The second one is the logistic regression, which is exactly the same, but with a different activation function called the sigmoid. And the output here is a value, is a real value between 0 and 1, which we can somewhat interpret as the probability of being into class 1 given x. These two networks can be made k-class. So by having k output, here we have 3 outputs, so we assume you would have 3 classes. And the perceptron would just take the output of the neurons there without any activation function and just keep the class or assign the class with the largest score. Whereas the logistic regression would use a softmax, which is the exponential of each neuron followed by a normalization function. So again, the output of that logistic regression can be seen as a conditional probability function. We've seen a series of two-class loss functions. So here we have the Perceptron Criterion, which is mathematically, so it's the sum over all wrongly classified sample V, which is exactly the same than this formulation here. And if you have add a 1 there, this leads to a very well-known Inge loss or SVM loss. And if you have a logistic regression, then you would use a cross-entropy loss, which involve the logarithm of the output of your system. In the case of k-classes, well, it pretty much is the same idea. So you have the multi-class perceptron criterion. If you had the 1, that becomes a SVM loss or Inge loss, and still you have the log of the output for the cross-entropy. And each time you minimize a loss function, I say each time, it's almost each time you minimize a loss function, you need to define a certain constant time a regularization term. If you do not add a regularization term, your neural network will very well suffer from what we call overfitting, which is a concept you have seen before. Now, the optimization is still a gradient descent, a stochastic gradient descent, where you iterate for a certain number of time, and then at each iteration, you go through every element in your training data, and for each element, you compute the gradient of the loss and move your weights in the opposite direction of the gradient of the loss time a learning rate. And again, the learning rate is an hyperparameter, as well as the lambda value here, the constant there, which is also an hyperparameter that you need to a priori predefine before training your system. Now, so far, we have seen linear classifiers, 2-class and n-class linear classifiers. Obviously, eventually we would like to have nonlinear classifiers. And the only way of doing this with a neural network is to go deeper. And this gives rise to what the so-called deep learning or deep neural networks. Now, as we mentioned before, when we deal with nonlinearly separable data, there are three classical solutions to that problem. First, we may acquire more data. That's what we illustrated before. Second, we may use nonlinear classifiers. It is not the topic of this presentation, but you could use, for example, random forest, for example, which is a nonlinear classifier. But third, we may transform the data. So take data that is nonlinearly separable and transform it into data that is linearly separable. And this is what deep neural nets do. So let's go back to a configuration that you are now familiar with, which is a 2D set of data, x1, x2, let's say the body temperature and cardiac frequency, two classes, and a linear neural network. So it's in fact a linear logistic regression, which embodies a dot product followed by a sigmoid function. So here we have the input layer, 3 neurons, and the output layer, which has 1 neuron. We mentioned before that we can add more than 1 neurons to our neural network. We did that before to account for, let's say, 3 classes. But for the sake of this example here, we'll just add 3 neurons, which all come with a sigmoid activation function. So each neuron computes a dot product. This is what an artificial neuron does, followed by a sigmoid function. So the output of that neuron would be a real value between 0 and 1, because the sigmoid returns a value between 0 and 1. Same thing for the second neuron, same thing for the third neuron. Now, mathematically, if you compute this, at the end, these 3 dot products can be summarized by a multiplication by this matrix with the input vector 1, x1, x2, as we've seen before. And the result of that operation is a 3 by 1 vector that we may feed to our activation function. And this would return a 3D vector. And in short, that would be, so what's going on here can be summarized like this. So we have a matrix W, which contains 3 by 3 sets of parameters, 3 by 3 because we have 3 neurons here and 3 neurons there, times the input vector, which is a 3D vector. And then you feed this to a sigmoid function, and that sigmoid function would return 3 real values because it is fed with a vector of 3 elements. Now, mathematically, nothing prevents us from taking the output of those 3 neurons and combining these output to a 4th neuron here, which would essentially compute the dot product of these 3 outputs with the 3 weights that you have here. Now, if you do this, followed by a sigmoid function here, the output of your network would be what? It would be the multiplication of W times X for this layer, followed by an activation function because of that sigma over here, times W here, which is a dot product, and with the final sigmoid, which would be here. Now, this neural network contains now 3 layers: an input layer, a so-called hidden layer of 3 neurons, and 1 output layer. And this machine, or this neural network, is still a 2-class classification method. Why? Because the output is a sigmoid, and the sigmoid returns a value between 0 and 1. And if the output here is larger than 0.5, then you know that you're in class 1. And if it's lower than 0.5, you know that X is in class 0. Usually we come up with a visual simplification and do not write the weights associated to each little arrows here, but have a configuration that looks more like this. So this machine, already you have a feeling that the output here is a nonlinear function with respect to the output X, because you have a series of linear, nonlinear, followed by linear, and then again nonlinear operation. So these 2 nonlinear operation makes this overall function nonlinear with respect to X. So if your data is nonlinearly separable, already you have a feeling that this function here, which is going to be trained, so each element W, and so the vector W1 and W0 are going to be trained with the gradient descent algorithm. So of course we can add a bias neuron if we want, because according to just that output neuron, this output neuron does what it does the best, which is a dot product followed by a nonlinearity, and this very operation is nothing more than a linear classification. So it's linear classification with respect to the previous output, but overall the system is nonlinear. So I hope this is not too complicated. We'll see an example in a few slides. So this network contains a total of 13 parameters. Why 13? Because we have 13 arrows. Here we have three neurons that connect with 3 neurons. So 3 times 3, it's 9, plus 4 neurons that connects to 1. So plus 4 times 1. So that's a total of 13 neurons. Mathematically, nothing prevents us from increasing the number of neurons in the input layer. So here we now have 1, 2, 3, 4, 5 neurons plus a bias. In this case here, we would have 5 times 3 plus 6 times 1, so a total of 21 parameters. And the more parameters that we have, the better the system will be at recovering a nonlinear classification function. So here is an example of no hidden neurons. So here we have a system that tries to separate these green dots from the red dots, which are obviously non-linearly separable. But since we have no hidden neurons, this system cannot perform well. In fact, it suffers from a phenomena called underfitting. So the system is too simple for the data. Here I tried with 12 different hidden neurons, and this gave a pretty good result. So overall, it works very well. And here I've put too many hidden neurons, and now the system is starting to overfit by having this very exotic shape overall. And I strongly recommend you to go on this page and to play along with those parameters. This is a Node.js online demo that anyone can play with. So again, deep neural network like the one we had also benefit from the the advantages we have seen before. So like any neural network, it can account for an arbitrary large number of input variable. So the more input variable you have, the more parameters your overall system will also have, which eventually could be a problem. But mathematically, nothing prevents you from having an arbitrary large k value here. So this network would have 5 times k plus 1, so 1 is the bias here, plus 1 times 6 parameters. So if k is very large, then you'll have a lot of parameters in that system. Also, nothing mathematically prevents us from adding an extra hidden layer. So in this case here, we would have this machine there that take the input vector, multiplies it by a matrix W, which is 5 times k plus 1. K plus 1 is the total number of neurons in the input layer. That would give us, followed by a nonlinearity, so this is what we have here, times a matrix W1, followed by a nonlinearity, times the vector V2 that we have here, followed by a sigmoid nonlinearity. So adding an extra layer ended up adding a matrix multiplication followed by a nonlinear activation function. So here we have even more larger number of parameters because we have more layers. And we could go like that. Here I created an arbitrary neural network with 4 hidden layers. Each hidden layer are matrices of size 5 times k plus 1, 3 by 6, 4 by 4, 7 by 5, and the last layer is in fact a vector of dimension 8 because we have 8 elements here, 8 neurons here, times 1 output neuron. And as you can see, the overall system implements this function here that contains lots of nonlinearities, and so this overall system is highly nonlinear. So it's very good at separating data that are nonlinearly separable. But if you keep on looking just at the last layer, this last layer only computes a dot product followed by a sigmoid. So if you just look at this output neuron, this is a linear classifier. So the more hidden layers that we have, the deeper the networks get. And now you understand what it means to have a deep network. It means a network with lots of hidden layers. And the more hidden layers that we have, the more capacity we have. So what's going on here? In fact, we have a system like this, a multi-layer perceptron, which inputs a vector x, which has k plus 1 dimensions, followed by all of these operations, matrix times vector with a nonlinearity times a matrix with a nonlinearity times a matrix with a nonlinearity times a matrix, and then at the very end we have a linear classifier. So how do we understand this? You know, I said before, one way of dealing with nonlinearly separable data is to transform the data. Well, that's what a neural network does. For example, if we take here points that are in a two-dimensional space, so the horizontal axis would be x1, the vertical axis would be x2, and as you can see here, we have one hidden layer and then a second hidden layer, and the second hidden layer has two neurons. So we'll look at the output. If you plot the output of those two neurons once the overall system is trained, we see that each red point now lie into this scatter plot, and each blue point lies into this scatter plot. And as you can see, these points here lie in a new dimensional space that has nothing to do with the first input dimensional space, but this space is linearly separable. So what our system has been, so our deep neural network has been able to do is to take these points in the input dimensional space, project it into a new dimensional space here, and the last layer is only a linear classifier. That's a way of seeing how neural networks work and why they're so effective at doing this. And they did that throughout just a training process. So of course, a deep neural network can account for k classes by having k neurons at its output. So if we do this, we can train this neural network with the hinge loss, for example, as we have mentioned before, multi-class hinge loss, or so-called SVM loss. And if we put a softmax at the output, so an exponential followed by a normalization, then we can train the system with a cross-entropy. And this cross-entropy is something that is very usual, as you will see during this class. So in conclusion, we have seen linear classifiers. We have seen that linear classifiers are simple linear operations, and these linear operations are dot products. And this dot product led to the very first definition of a neural network, which is the perceptron. And if you replace the activation function of the perceptron with a sigmoid, you get a logistic regression, a linear logistic regression. We have seen how to account for k classes and what kind of loss functions can be used to train these neural networks throughout a gradient descent. And we finished with a so-called multi-layer perceptron, which allows to separate data that are non-linearly separable.